In this video, we're going to follow on from the example in the previous video of how to use a one-dimensional bar element to model a two-dimensional truss. I'm going to start off by importing a few libraries we need. Numpy, np. I also want to import the norm function. This is actually from numpy.linear algebra. Import norm. This takes the magnitude of a vector. We also want from scipy, lin-alg, import the eig-h function. We've seen this in a previous video. That returns for a given k and m set of matrices, it returns the eigenvalues and eigenvectors. And since we'd like to plot something, we'll import matplotlib, actually pyplot as plt. Alright, I'm going to give this code a little bit more structure than I've done in the past. I'm going to define a main method, and then, being Pythonic, we'll say that if name is equal to main, I don't want this to cause confusion. This is just what you do in Python to reuse code. The idea is that if I run this file directly, it will call the main method. If I don't run it directly, if I were to import it like this into another piece of code, it would just import the methods that I've created without actually running it. And that's all I want to say about that. So I'm going to proceed by adding some comments to the main method. And again, this follows on from the previous video. First thing we need to do is the problem setup, followed by determining the global matrices. Next thing we want to do is find the natural frequencies, followed by calculating the static displacement of each element. From that we can determine the stresses in each element. And then finally we want to output the results, whatever we want to display. Let's fill in a bit of meat here. So this will return the properties. I'm going to call setup, I'm going to return properties. And let me just put this up top. Return properties. Obviously there's a bunch of meat that needs to go in here, but we'll save that for later. Determining the global matrices, I want to get m, k, and f, which is a vector, which is really just a one-dimensional matrix, and we'll create a method called getMatrices. We'll feed that with properties. Let's define that up top. And this is going to return, whoops, what did I say, m, k, and f. Alright, finding the natural frequencies, we'll call that, we've done this previously, evals and evex, and that's just using the eig-h function that we imported above, and I put in k and m in that order. I can then determine the frequencies, which is just the square root of the eigenvals. We'll use the numpy version of square root for this, since that does it element by element, and also it's really fast. In general, I recommend using numpy functions because they are optimized. Then what we want to determine is the displacements, and the displacements is the inverse k matrix, the static displacement, that is the inverse k matrix times the force vector. And how we write that is x, static displacements, and again we'll use numpy linear algebra, and we'll use that to invert the k matrix, and then we want to multiply that by f, so dot f. And just to be clear, this dot accesses the method, and this method dot is actually the dot product. So we're multiplying k and f matrices together, or inverse k and f, in the dot product sense, which is how you would expect to do it. Stresses, we'll create a function called getStresses, and that will take both the properties and the static displacements. Let's define that above. And this is going to return the stresses. and then finally output the results. This doesn't return anything, it's just a method we'll call show results, and we're going to feed into that the static displacement, the stresses, and the frequencies. And again, we're going to define this up here. That's not going to return anything, or we can just put in return. Make it a little bit more complete. And there you have it. This is the main method of our code. There's nothing more to actually be done here in terms of the main method. Everything else is going to be about putting the meat in on these methods up above, maybe adding a few more methods. Okay, so again, problem setup, determine the global matrices, find the natural frequencies from those global matrices, calculate the static displacement of each element. From the static displacement and the properties, we can get the stresses, and then finally we want to output the results. So we'll proceed by defining the setup method, and let me just make a bit of space here. So the first thing we'll do is define the coordinate system, and we do that by, let's say, x-axis, we'll call it, is equal to numpy array of 1, 0. Similarly, I'll just copy and paste this. The y-axis is just 0, 1. Next, we'll define the model as described in the problem. And how do I want to do it? First of all, we will say the nodes are equal to, I'm going to use a dictionary for this. Node 1 is 0, 10. Node 2 is 0, 0. And node 3 will be 10, 5. Let's define the degrees of freedom. And those are equal to, here's I think the best way to do this. We'll define it at each node. So we'll say at node 1 the degrees of freedom are 1 and 2. Whoops. At node 2 the degrees of freedom are 3 and 4. And at node 3 the degrees of freedom are 4 and 5. 5 and 6. Okay. The elements themselves, how do we want to define the elements? Again, using a dictionary, element 1 goes from node 1 to 3, and element 2 goes from nodes 2 to 3. This is somewhat arbitrary the way that I'm setting this up, but I find that by using dictionaries it makes it fairly useful. We also have some restrained degrees of freedom, and I'm just going to create those in a list. 1, 2, 3, and 4 are the restrained degrees of freedom. These are fixed, as shown in the problem. And then finally we have some external forces. And I'm going to do this in a similar manner as above, that at node 1 the forces are 0 and 0, at node 2 the forces are 0 and 0, and at node 3 the forces are 0 and minus 200. And just because I like things to look neat, I'm going to space this out. Oops, let's do it this way. All right. So those are the actual model definitions. The next thing is to look at the material properties. In this case, we're using a carbon steel. It's AISI 1095 carbon steel, also known as spring steel. Why? Because it's typically used in springs. Pretty high yield strength, very high toughness, tends to be very elastic. We'll define the densities, and this again is for each element independently. So for element 1 and 2, they're actually the same. 0.284. That would be pounds per square inch. 284, excuse me. And similarly for element 2 is 0.284. And this is a typo. Densities, okay. And the other thing we need are the stiffnesses, or the Young's moduli. And similarly, it's, what was it? It's 30 times 10 to the 6, so 30e6. And again for element 2 is 30e6. For the geometric properties of the elements, in this case it's just the areas of each. We'll call it areas and set up a dictionary that says element 1 has an area of 1. This would be inches squared, and element 2 has an area of 2. And then we'll do a quick calculation. Number of degrees of freedom, the total number of degrees in the whole system is actually just 2 times the number of nodes. Well, the number of nodes can be found by taking len of the nodes. And just to be a real stickler about it, I'm going to put in some assertions here just to make sure we've defined everything correctly. Assertions. So the first thing we'll assert is that the length of the densities is equal to the length of the elements. So we need a density for each element. Well, that makes sense. And this alleviates any potential typos above. We'll also say that that's got to be equal to the length of the stiffnesses. And we'll say that's also going to be equal to the length of the areas. So it's really saying for each element we need the same number of densities, stiffnesses, and areas. That makes sense. We'll make another assertion that says the length of the restrained degrees of freedom has got to be less than the number of degrees of freedom. You can obviously not have more restrained degrees of freedom than numbers, and even if they're equal, then the problem is trivial because all the displacements are 0, obviously. And I'm going to put one more assertion, which says that the length of the forces is equal to the length of the nodes. We need a force for each node. All right, and then the final thing that we're going to do is we want to return these properties, and I'm going to do that by putting them all into one giant dictionary. So, how do we do that? First of all, x-axis, colon x-axis. Similarly, the name y-axis will be given to the y-axis. Oops, what am I doing? There we go. We'll call the nodes nodes. We'll call the degrees of freedom degrees of freedom. Let me just cut this a little bit because it might be running off your screen. Actually, we can leave it there, degrees of freedom. And we do this with a backslash, by the way. Continue on the next line. Elements. Elements. What else? Restrained degrees of freedom. So all I'm doing is taking all the things I defined above, and I'm giving it the name. Whatever I call the variable is the actual name I'm going to give it for the key in the dictionary that I'm creating. Forces. Should have quotations around it. It's a literal. Number of degrees of freedom. Again, we're going to break the line here. densities, stiffnesses, and finally the areas. So again, what have I done here? I've taken everything I defined above, I'm returning it as one giant dictionary, and then down below, when I call it, I'm going to assign that to properties. So properties is going to be a dictionary containing all these properties, which I can access by using the correct key. All right, and then we're done with this. I can collapse that. So what's the next thing? The next thing, and this is really the bulk of it, is this get matrices routine. What do we do for the get matrices routine? Well, we follow the method that I presented in the previous video. Probably easiest, let's see how I want to do this. All right. So what we need to do is we need to construct the global and stiffness matrix, the global mass and stiffness matrices. That's our goal here. The first thing we want to do is we want to access, we've passed properties to this routine, we want to access some of the properties that we're going to need. So I'm just going to say number of degrees of freedom is equal to properties, number of degrees of freedom, nodes is equal to properties nodes. We need the elements, which is equal to properties elements. We need the forces. Since we need to create the force vector 2, that's equal to properties, properties forces, and that's not force, but that is forces plural. Since each one of these is a dictionary, remember that properties is a dictionary of dictionaries, and now we want to access the dictionary of each one of these variables. Areas is equal to properties areas, x-axis and y-axis. A little bit tedious, but I think it's best for writing good compact code actually in the final analysis. And similar, y-axis is equal to properties y-axis. And I'm just going to space this out a little bit so that makes it a bit more readable. Okay, and then what I'm going to do is I'm actually going to plot the nodes just to make sure we've got it correct and we can see graphically that this is so. So I'm going to go plot, how do I want to do this? Let me create another function, a method called plot nodes, and we're going to pass the nodes into that. All right, I'm going to go above this one that I'm working on and say define plot nodes. It's going to take nodes, as we just said, and then what do I want to do? I want to take the x and y coordinates for each of the nodes. So I can do it this way. I can say for I in nodes dot values. And what do I want to do? I want to create a list from this. So we can do this Pythonically. And the way we do that is we'll say that x is equal to I0, which is the x value. So what have we done? We've basically taken I in nodes of value. I is x and y, so we say that the 0th component, which is actually the first one, it's 0 indexing, those are your x's, and we want to create a list, and we're going to do almost the identical thing for y, the only difference being that we're now taking the thing at index 1, taking that value. I'm going to define something here, and just from playing around with it, I determined that we want size equal to 400, offset is equal to size divided by 4,000. There's no great magic here. This is just from playing with it, having done it ahead of time. You'll see in a second where these come in. So what do I want to do? I want to take PyPlot and I want to produce a scatter of X and Y. I'm going to make the color of this equal to yellow. Size is equal to size, as I've defined it just above here. And then the only other thing I want to do is a Z order. Z order is equal to 5. The idea of the Z order is really a layering effect. Any objects in your plot that has those with a higher Z order will appear in front of those with a lower Z order. That shouldn't be too confusing. The higher the Z order, means it overlaps anything with a lower Z order. And the 5 is arbitrary. I could have used 2. I just like to space it out a little bit. And then what I want to do is I want to plot each of the nodes. So I say for I, how do I want to do this? Node 1 and location in enumerate. I want to zip the X and Y's together. So I've zipped X and Y's into a location and then I've enumerated it and I've pulled that out into 2 values, I and location. Location 0 will be the X and location 1, index 1 will be the Y. And on my plot I want to annotate the name is I plus 1. Remember, it's 0 indexing, so node 1 is actually I equals 0. So to make sure it shows as a 1, I'm going to add 1 to it, I plus 1. And where do I want to plot it? The X value would be location 0 minus the offset. Since I don't want it to appear on top of the dot, I want it to appear next to it. And similarly for location 1. So in each case I'm taking the X value and Y value, which puts it on the node, and then I'm offsetting it slightly because actually this is not the node, this is an annotation, which is the label. And in each case it's I plus 1, so I will be 0, 1, and 2, so the nodes will be labeled 1, 2, and 3. And I need to give this a Z order, and following on from what I said before, we'll give this a Z order of 10 so that this would overwrite anything underneath it, or anything else that I've plotted. This has a Z order of 5, so the nodes themselves would appear under the annotations in the event that they were overlapping. Okay, let's continue. That's really it. So in terms of the plot nodes, we're done with that. Okay, so once we've plotted the nodes, we think about how best to do this. Well, now we want to find the matrices by cycling through each of the elements. In a previous video, we showed how to do this. There's a little bit of difference, however. We're going to start off by defining our global matrices as just zeros. So we want to create a matrix that's full of zeros, that's the size of the global matrix. How do we do that? Excuse me, NP zeros, and it's just number of degrees of freedom, whoops, by the number of degrees of freedom. We're going to do the same thing for the K matrix. Now we're going to cycle through each of the elements. So we'll say for element and elements, what do we want to do? First of all, we want to find the element geometry. So we'll say, what is the point that the element is from? Not the node, but the actual point. So we'll say from point to point, and the associated degrees of freedom will be returned by something we call points, which is just a new method we're about to define. And that will be the element and the properties. Copy this up above. So we're going to add a definition for this new routine, and it's going to return, I made a mistake down here, this should be an equals, and it's going to return these three values in that order. TURN. Now we need to fill in some meat here. So we need to take the element definition, and we need to take the properties, and from that we should be able to find the point that this particular element starts at and ends at, and the associated degrees of freedom with that element. In other words, there are 2 degrees of freedom on the from point, another 2 on the to point, and we should have a total of 4. The way I want to do this is to say that, first of all, the elements is equal to properties of element. Excuse me, properties elements. I'm just pulling this straight out of the properties definition. What is the did that plural? Excuse me. Same thing for nodes. And the same thing for degrees of freedom. So the first thing is we want to find the nodes that the element joins or connects. How do we do this? From node is equal to elements. Let me just go back here. Remember that we define something called elements that says element 1 goes from nodes 1 to 3 and element 2 goes from nodes 2 to 3. Once we know what nodes 2 and 3 and 1 are, we can go to our nodes dictionary and find out what the actual points are associated with that. All right, so let me see if I can leave that in view while I do that. So we want to take the node, the from node, or the first node associated with that element, and we'll say this is equal to element index 1, excuse me, index 0. And similarly, the to node is equal to elements of the particular element in question. Remember, we've passed that in here to our method, and we just want position 1. So what have we done? We've found for this particular element what the from and the to node is. Let me just say that again. So in the case of the first element, element 1, we go up to elements, and we see, oh, element 1 goes from element 1 of node 1 to node 3, and by using the 0th and 1th value, we've defined the from and to node. Okay, hopefully that's not confusing. Now we want to find the coordinates for each node. And I'm going to call that from point and to point. The point is the actual coordinates. So now that we know the node, we can find the coordinates. How do we do that? I want to do that as an array too. So we'll just use np array. And it's nodes of from node. Does that make sense? So we go up to nodes. We know what the from node is from here. We go up to nodes above, and once we know the from node, we can read what is the coordinate. And since it's a coordinate, it's an x and y value, I actually want to store it in a numpy array. This is going to be exactly the same, except it's the to node. Okay, hopefully that hasn't caused any confusion. Find the degrees of freedom. Find the degrees of freedom for each node. Now how do we do this? We'll say degrees of freedom, DOFS, is equal to degrees of freedom based on the node. the from node in this case. Then what we want to do is take our degrees of freedom. We want to extend it. And I explain that in a second. Degrees of freedom of the to node. Okay. So the from node is a list. In each case, the node gives us a list, and this gives us a list. I want to create an array with both lists, but before I do that, I want to flatten these lists. In other words, I just want it to be one list containing all four of these nodes. Using the extend on a list actually flattens the list. Okay? So again, what have we done? We've gone to degrees of freedom. We know that at node 1, for example, we get the list 1, 2. At node 2, I've got to take this comma out, that's a mistake. We've got a second list, and instead of having two lists, I actually want to flatten those into a single list, which is why what I've done is degrees of freedom here is a list, and instead of appending to the list, I've extended the list, and that has the effect of flattening the list. And then finally, I'm going to say DOFs. I want to convert this into a numpy array, where I'm going to put DOF in there. DOFS. I left out an S here. So again, take the list, which is the coordinates of the first node. Not the coordinates, but the nodes, excuse me. Degrees of freedom. Node 1 has 2 degrees of freedom, it's a list. Node 2 has 2 degrees of freedom, that's a list. I'm saying take the one list, extend it by adding the other list and flattening it, and then convert it into a numpy array. Okay, this is a little bit tedious, but once we've got this set up correctly, it makes everything else a lot clearer. And then finally, I'm just going to return this. We have that statement already. I'm going to return the from point, the to point, which I've calculated over here, and the degrees of freedom. Okay, and now points is done.